Great. So a lot of interesting ideas here. Let's see, who wants to start addressing the panel? Yeah.
Jared, that was really interesting for what it could, for like the tasks that could be completed, and the part about inferring the reasons that the parent had, I totally missed, because I feel like, if I see a parent move a stool, like I can totally imitate it without understanding why the stool needs to be moved. And I felt like that robot, putting the chip in could be in the exact same situation. They might have no idea that the chip's even broken. If they're just imitating. So like, how does like inferring reasons, get approached?
Yeah, thank you. Good question. So, yeah, I did mention a little that there's a lot of knowledge engineering and background knowledge, and there's a certain form of cause-effect reasoning in that, but it's all kind of action and task oriented. It's like, if I want to perform this sort of high-level action, this is the low-level action that does it. It doesn't really inspect states and facts in the states so much to see which facts are changing. So that's something we definitely want to go for. But I think the main form of reasoning, as opposed to background knowledge, is that kind of parsing problem. Like, if the robot put something down, is because it actually had to go there, or because they just had to free up this gripper to do something else? So in that way, it's doing some reasoning. But a human does have to provide the big database of all the intentions and the subsequences they might cause.
Which could be loaded in RCs, right? It's just something that's just a syntax that I pictured in my head.
Yeah, certainly.
But it could also be like observed and generated through observation, if not the exact observations that are being imitated.
Yeah, so I definitely agree, and we want to go in that direction, that it's learning from experience more. But I think that has some challenges too. If those higher level intentions that I hand coded are hidden, even if it's just observing a new sequence of actions, how does it really form this structured internal model? So that would be non-trivial.
No, it's very interesting. It's a very satisfying answer. Thank you.
Thanks.
Yeah. Yeah.
Okay, quick question, especially to the last two speakers, because it was nice to see one, like the talk with the cognitive event calculus, and after this Nico's talk. To both of you, how do your formalisms actually complexity-wise work? Like, starting out with event calculus back in the time of Bob Kowalski, this was pretty much prologue stuff. Like, this was really quick, this really compiled nicely. But when you throw in modalities, aren't you actually so far out of provably being quick? So how do you get your real-time reasoning then? Or why are you sure it works? Same to Nico. So you had the beautiful moment where you said, well, okay, it's NP hard, NP complete, one of the two. But it's not that bad, because all others are worse. Nonetheless, if you actually would now say, okay, I want to build a general AI which can move in a general environment, which can real-time react, you don't want to hit an NP hard problem, right? Or at least you don't want to hit the bad area of this NP hardness. So what's your take on this? Do you care?
Well, I guess I'll go ahead and go for that first. Is it working? Okay. And I'll say that speed absolutely is a concern for me on the matter end, and to an extent, this is sort of a Hail Mary in that we don't have matter using CEC codelets yet. We're still designing the CEC AC logic. So our hope is that by dividing the proving in between codelets, because individual codelets can be focused on a specific inference rule, a specific task, that so long as when you set up proofs through matter, you intelligently select, or I guess the AGI intelligently selects which codelets to use, that the speed will be, you'll get the speed that way. It'll be sort of a faster reasoning if you're only going through the matching of a few different rules. But you're absolutely right that speed is a concern. That's actually something I'm dealing with now, because I'm trying to write a form of, at least a generic abstract interface for codelets that'll make it very easy for, say, a philosopher to write their own codelet, or a logician to write their own codelet. And about the fastest ways to do that in a way that truly captures the meaning of the inference rules goes back to that really slow, really grinding semantic analysis. So, to an extent, it's a hope that the codelets help offset that, but it is a problem we're aware of and not quite sure how to solve yet.
So does this work, do you mean? Okay, okay, I mean, I agree that NP completeness or NP hardness is probably not what we should shoot for, but I mean, the NP hardness result really is when you want to find an optimal concept. And if you just want to find a nearly optimal concept in some heuristic sense, then it's actually possible in polynomial time. So, I mean, if you think about human thinking, then I don't think that humans in general find the optimal solution, right? But rather, they perform some kind of heuristic reasoning in the sense that they try to, well, I don't know what they do, but...
Let's call it satisficing.
Right. I mean, you have some intuition and you try to, you just follow your intuition, and in this way you get some solution, but you have no idea if it's a good solution or the best solution. I mean, your intuition suggests that it's a good solution, but you never know, right? I mean, for instance, if you consider things like the traveling salesman problem, where you want to find the shortest path or something like that, then people or humans usually have a good intuition for what is a good path, but they have no idea how good it really is. And of course, this also depends on things like whether you consider Euclidean distances or completely different things, and then humans probably have no idea what a good route might be, right? If it's not longer like in your intuition of regular distance, then you probably wouldn't even find some nearly optimal solution.
Thank you.
Quick thoughts. You had talked about forgetting in the context of emotion or that. Did you only need it for that, or was that just for an example?
Yeah, there are two basic situations when structures can be forgotten in this system, and one is emotional situations, and a situation can be emotional even though, I mean, if it has an emotional importance, like let's say red isn't perhaps emotional in itself, but when combined with red berry, for example, it can become emotional. So then the notion of red is not going to be forgotten. And the second situation when it will forget is when the concept isn't used very often. So that's, yeah.
Okay, I'm particularly interested in like where I parked my car 3 days ago as opposed to yesterday or now. Is that integrated into this?
Sorry, I didn't hear.
Yeah, the concept of forgetting in the context of where I parked my car last week, or where I parked it 3 days ago as opposed to where it's parked now.
Yeah, right. So where you, the information that you parked your car in some place 3 weeks ago will become older and not useful anymore, and then it will eventually wither away.
Okay.
We have Paul. Okay.
So I have a question each for Pan and Klaus. For P, the question is, so the difference between reasoning and learning typically in a cognitive model comes about because you've got working memory versus long-term memory. Reasoning changes working memory, learning changes long-term memory. Logics typically don't have that distinction, and so if you're just changing beliefs, you can't really distinguish reasoning from learning. I was wondering if that's essentially what's going on in what you were talking about. And for Klaus, the question is, so you're building these deep networks, but are you doing deep learning in the sense that you are learning the hierarchy of parameters to be able to do the kinds of classification that these systems are able to do?
I know this is probably a controversial design decision, but from the very beginning, in ours, there is only one memory. So one thing we do not distinguish is separate learning working memory or short-term memory from long-term memory. But we believe, the belief is we keep that distinction instead of use two separate memory, but instead use two kind of like a matter of degree or some kind of quantitative difference. So what we have is in the memory, everything has several value attached. One I already mentioned is a priority. That is, next moment, what's the chance for this thing to be used? Another thing is what we call durability. That's actually a different item has different forgetting rate. So something you can activate at priority become pretty high, but at the same time it will decay pretty fast. So that kind of thing is very similar to what we say working memory phenomenon. So I know there is tons of psychological evidence supporting the distinction of this tool, but I haven't been convinced that we have to separate piece of memory in ATI instead of using one uniform mechanism, but at the same time capture both. So there's some benefit because, for example, I don't have to decide when to move something from working memory into long-term memory. Because when the durability becomes high enough, something gradually become remembered longer. So there's no clear cut, who is on which side. On the same line, there's also, you see, we don't have a separate, say, semantic memory from procedural memory or that kind of thing. Just because, but that distinction is still there. There's some knowledge which is procedural by nature, some knowledge are declarative by nature, but they can all be integrated into the same memory. That's basically.
So would you say that there's a continuous kind of a emergent short-term, long-term distinction?
Yes,
Yeah.
it's just a matter of degree. Yeah, semantic procedure is not a matter of degree anymore. It's different type, but they can still be stored together into the same structure.
Yeah, so the question was about deep learning, in what whether that was that's what's going on in those transparent networks, and it's quite different because deep learning, the ordinary kind of deep learning is presupposes the ordinary kind of networks with weights and backpropagation and so on, and I don't have that in the transparent nets, but they develop organically all the time, and in that way will be naturally created several layers, so in that sense it will become deep and hierarchical. And another thing is that sometimes when the compress rule kicks in, the networks will be rebuilt. So compressed will look for equivalent or lossy or non-lossy compressions of these networks. So it's basically about compressing propositional formulas instead. And that opens the possibility of finding new ways of compressing and new ways of building general concepts and feature sets that are perhaps not captured by the ordinary kind of deep learning algorithm. I don't know, but that's a possibility.
Anyone else? Questions? Yep. Here.
Nico, with the stuff you're doing from Fauconnier, I mean, I guess I feel like I have to fill in a little background. I mean, Fauconnier's basic notion was of a mental space, and there are two mechanisms, blending and compression, that are general ways of producing new mental spaces. And his claim is that basically all of human thinking is organized in that. That's how you do essentially, the way you solve problems is by manipulating these spaces and combining things, and it's a predictive model of learning. So the mental space has to be populated both by behaviors and by objects. So when you're blending two things, the question is both how do the behaviors of the two things, so to say it's a centaur, you have to properly blend it, you have to say what it does as well as, it has the head or the body, upper body of a person and the lower body of a horse. But, so if you really wanted to, it's not a logic-based approach, it's essentially saying you're creating a very particular type of frame in which you can then manipulate objects. He calls it run a simulation, so like if you want to find out whether somebody coming down a mountain and somebody going up are going to meet in somewhere in the middle or not, you sort of can make a blend of the two of them going up, one starting at one point, the other one at the other, and then see if they meet together. And his examples are pretty compelling. The question though is, what sort of logic is there, or are you really replacing the logic with those three operations, the blending, compression, and simulation? So are you working towards developing a systematic approach to generating mental spaces?
No, that's the short answer, no. It's really
Why
about,
not?
it's basically about computing conceptual things.
Okay, so we're running out of time. If there is one last question, we have time. Okay. Otherwise, we'll thank the speakers once again. Thank you for coming.